Thank you for joining us today for the third installment of Food at the Tipping Point, Ways Forward from a Food System in Crisis. From past themes of resiliency to innovation and now to action, this year's speaker series focuses on the urgency to act. With extinction level losses of biodiversity, more frequent and severe extreme weather events impacting all stages of food systems, rising food insecurity, and growing political tensions, a widespread and dramatic change is urgently needed in our food systems. Join us every other Thursday where we bring together community leaders, researchers, and on-the-ground experts for real-life inspirations and solutions to the problems that we face. This series is presented by the Center for Sustainable Food Systems at the UBC Farm, generously sponsored by RBC Royal Bank in partnership with the UBC Faculty of Land and Food Systems and the BC Food Web. The Center for Sustainable Food Systems at UBC Farm is a teaching and research center which is a local to global food hub working towards a more sustainable food secure future. Our mission is to innovate from field to fork to achieve resilient, thriving, and socially just food systems for everyone. BC Food Hub is a web portal projected to aim to increase access and connection to current research and other resource materials. In addition, it aims to encourage innovation between farmers and researchers for future project collaborations. The UBC Faculty of Land and Food Systems is a world leader in research and teaching about the sustainable and healthy food supply. Today's topic is biomaterials, the future of food packaging and single-use plastics. We are fortunate to have Ms. Loveys and Amanda here with us today to discuss both the potential and challenges around biomaterials in tackling the plastic crisis, as well as to give us an in-depth look at some of the great innovations that are happening in this field. As a housekeeping item, after each panelist gives a brief presentation, we will move on to the Q&A portion of the webinar. If you have any questions for the panelists, please navigate to the Q&A tab at the bottom of the Zoom panel and share your questions with us. Also, feel free to upvote others' questions by clicking on the thumbs up symbol. After we see your questions, we will be taking up some of the questions during the Q&A portion of the webinar. With that, first I have the honor of introducing Loveys Chale. She is the owner and managing director of the circular bioeconomy research consulting firm Regenerative Waste Labs. She is a sustainable material researcher with 8 years of experience developing circular economy-based solutions that recover value-added products from organic waste. In her work, Loveys advises businesses on circular product design, closed-loop recovery strategy, and how to communicate the value of circular products. She leads a technical team of researchers who develop novel waste management and circular recovery technologies. Thank you, Loveys, and over to you for your presentation.
Thank you. Thanks so much for that introduction and the invitation to speak at this event today. Really looking forward to sharing some of the work that we're doing at Regenerative Waste Labs. But yeah, so today I'm going to talk a little bit about kind of a higher level description of some circular biomaterials, just to kind of set the stage before we hear from Amanda, who's been making some amazing new materials out of her PhD thesis. So Regenerative Waste Labs, we're a consulting firm. Let me just make sure the slide changes. There we go. So we're a research consulting firm that couples testing with advisory services. We really are passionate about sustainability, and we really envision a world where waste can be regenerated into the products that are healthy for people on the planet. And so the work that we do, we really try to support sustainable production and consumption by helping businesses to design truly sustainable products and also to find value in organic waste. And so being a consulting firm, we work with a lot of different businesses, and we really see that their businesses are taking a variety of different approaches to drive sustainability. And so on one side of the spectrum, we have a lot of companies which are working towards circular economy solutions. And so here we have the value really being placed in restorative and regenerative design. So feedstocks which come from chemical and plastic production, and the end of life or the waste systems that are promoted within this system are reuse and recycling. On the other side of the spectrum, things which might be a bit more aligned with the food systems conversation is really businesses looking at bioeconomy solutions, so renewable and benign by design. And so feedstocks for this system are often centered in feedstocks from sustainable agriculture and forestry. And the waste systems that are prioritized or promoted within the bioeconomy are reuse and organic recovery, things like composting and anaerobic digestion. So where the waste labs really finds enjoyment and a lot of the work that we do is really at this intersection between the bioeconomy and the circular economy. And we can call this the circular bioeconomy. Within the circular bioeconomy, we're really trying to find opportunities to valorize waste or find ways to turn waste into products. And so the circular bioeconomy, the values it's centered on is renewable and regenerative by design. Feedstocks often come from the industrial, commercial, and institutional sector, or the IC&I, or from municipal organic waste. And so within the system, the waste streams or the end of life processes that are promoted are reuse, recycling, and organic recovery. So Regenerative Waste Labs, we provide services to support all of these different approaches to sustainability, but we do like to emphasize the circular bioeconomy above all other approaches because there's the additional benefit that plant and waste-based materials can provide, which bridges the gap between the bioeconomy and the circular economy and allows for both economic and environmental benefits of both of those systems. To take a bit of a deeper dive, so the circular model, so regeneration within the circular bioeconomy really facilitates the circular model. And so this is a model which encompasses all activities that can keep materials, particularly bio-based feedstocks, in use for as long as possible. And so here we have kind of the make phase where we're supporting circular design and sustainable production. Products then move into the use phase, and so we want to be able to share and maintain those products so we can keep that value in the circular system for as long as possible. We then move into a reuse phase where we can then remake and repurpose those products, so once again keeping that value inside of the circular loop. And finally, we end up in a recovery phase, so where we can recycle the raw materials or regenerate them back into our natural systems. So Regenerative Waste Labs really helps businesses in this regeneration kind of area, where we're taking, where we support circular design of products using plant and waste-based feedstocks. And we also validate the environmental performance at end of life. And so there's an interplay here when it comes to regeneration. We can think about it as how we can take waste to make materials and how we can make materials that will fit into our waste system. And so this is really the piece where the Regenerative Waste Labs works. And so if we think a little bit about this make aspect, when we're thinking about circular biomaterials, these are products that are designed for the biological cycle. And so these materials, there's kind of a spectrum of them, and I'll show you a bit about the landscape in just a moment. But so we can think about the waste streams that are generated from plants and food production, and we can think about extracting those natural fibers. And so we can imagine, there's things like coconut husks and hemp fibers, things where we can just mechanically extract and pull out those materials which are already part of our waste streams. We then have natural polymers. So these are often isolated through biochemical extraction. You can think about things like cellulose from plants, chitosan from sea creatures, silk proteins, and a compound called polyhydroxyalkanoate, which is a bio-based plastic. Then we can move to this kind of next stage where we're using a little bit more synthetic methodologies to create polymers or plastics. So here we can take we can extract the starting building blocks and use chemical synthesis to actually build these long chain polymers. And so some examples of these are polylactic acid or PLA, and we can also make bio-based conventional plastics like polyethylene through this method too. And kind of the final category of circular biomaterials is a composite material. So a mixture of all of these different three things which come before. And so you can think about mixing, coconut husks with a PLA matrix to be able to make a composite type material. And so by using composites, we're able to access a larger range of physical and degradation properties, which will allow that to fit into lots of different types of end-of-life streams. So some of the work that the Waste Labs is doing is really centered in waste regeneration. So we work with a lot of waste generators who are seeking opportunities to implement resource recovery technologies so that they can process their waste streams to allow for those waste users to utilize them in bio-based products. And so we've been working with a company called Terraformer Systems, who manufactures this on-site recovery technology to try to facilitate and create concierge programs to connect these waste generators with the technology that they need to then connect with waste users. And so plant and waste-based alternatives really have the additional opportunities to have more end-of-life options, things like composting, anaerobic digestion, environmental biodegradation like soil degradation for agricultural-based plastic. There's also the opportunity for chemical recycling and mechanical recycling. And with some of these products, you can also use it as animal feed. And so when we're using plant and waste-based alternatives, it really opens up a broader landscape of materials. So here we kind of have on one axis the bioeconomy. So this is bio-based versus fossil-based materials. And then on the other axis, we have the circular economy. So thinking about the end of life. So these could either be recyclable or compostable. And so we can kind of see here in this landscape that different products and plastics and materials, biomaterials, really fall on this very diverse spectrum. And so at our research space in the Falls Creek Flats, just down the road from Science World, we do a lot of research and client-based testing. And we've really revealed quite a range of degradation behavior for certified compostable products. And this really allows this diversity of circular biomaterials to have a various different applications. And so now we can tailor the type of material that we're using for the specific application and the specific end use as well. And so this really allows us to access reuse and recycling opportunities, as well as at the very end of its life, being able to be biodegraded or composted back into the ecosystem. And so I think it's probably a good opportunity here to talk a little bit about terminology, because often when we're talking about biomaterials, we're really talking about two specific subcategories of products, and there are intersections as well. We think about bio-based versus biodegradable. So biodegradable is really talking about the breakdown of a plastic piece, whereas bio-based is talking about the origin of a plastic. And so when we're thinking about the origin of plastic, ideally these materials are coming from renewable resources. However, they could also be coming from primary feedstocks like corn and wheat, though we want to prioritize utilizing waste streams to minimize the potential externalities that might come from using primary food feedstocks. And so there is certifications for bio-based products. And so you can actually have partially bio-based products. On the other side of the biomaterial spectrum is biodegradable products. And so these products could be fossil-based or bio-based, and it doesn't really determine that feedstock whether or not it's biodegradable. But biodegradable really means that it is a material that can be degraded by microorganisms to produce carbon dioxide and some sort of soil-like humic material. When we're thinking about certifications, there are certifications for compostable products. However, they cannot be partially biodegradable or partially compostable products. And so that's a bit of a difference between bio-based and biodegradable. And so some of the work that we do at the Waste Labs is also on just public education, because there's not too much understanding of how these products actually break down or how things break down in natural cycles. And so we designed this poster here. So we're just talking about, so this is from a project that we did last year, centering around bio-based materials and how they break down. And so bio-based materials break down through three key steps. They go through physical degradation, where the pieces get fragmented into smaller particles. Those particles then undergo chemical degradation through the action of enzymes and water. And then finally, when those polymeric chains are a small enough size, they can then be consumed by microbes to generate carbon dioxide and water and humus or soil. And so I might skip through these, but there are some, just a breakdown of the industrial compost certifications. So these certifications require a product to break down within, disintegrate to small pieces within 12 weeks, biodegrade to CO2 within 26 weeks. They also require a product to not have heavy metal or fluorinated chemicals present. And it also ensures that the product does go through plant toxicity and soil and vertebrate toxicity as well. And so there are definitely problematic plastics that are circulating the landscape. Lots of people wanting to shift to sustainable alternatives, but ending up kind of working with products which aren't really doing what they're supposed to be doing. One of those products is oxodegradables. These contain heavy metals and or peroxides to start the deterioration. So these have been proven to form persistent microplastics. So really wanting people to avoid the use of oxodegradables. There's also landfill degradable or enzyme degradable plastics. And so these often contain a microbe that's supposed to initiate biodegradation. However, after doing kind of deep dive and a review of a lot of the products in the marketplace today, we really haven't seen any evidence of significant biodegradation under realistic conditions. And so these are also a somewhat problematic type of material. So when we're thinking about composting, polyethylene films are difficult to collect and recycle. And it's been shown that these materials are actually the main product of contaminating compost operations today. So that's the plastic bag people are using. And finally, polystyrene is a challenging material as well. There is collection of expanded polystyrene, so the polystyrene you might be getting in when you're ordering a new appliance or things like that. However, because it's so light but so bulky, it does become environmentally burdensome to kind of collect that material to be recycled. But there are deposits and depots that have been created around BC and around Canada to actually collect the polystyrene. The polystyrene is the styrene itself, when it does leach out of the material, is an environmental toxin. So avoiding polystyrene is definitely of benefit. And finally, so the difference or some of the benefits, we can definitely talk about the limitations to the certified compostable products in that there is still not enough infrastructure to support the products that are entering the marketplace. But certified compostable products have been proven, at least in lab-based conditions, to break down within very specific timeframes. They have been tested for things like heavy metals and fluorinated compounds and have been shown to not have that environmental toxicity. And there are field testing programs which allow these products to be tested in larger scale compost operations, but that's not necessarily a requirement for the products entering the marketplace. And so there are definitely still limitations here. But some of the benefits of certified compostable plant and waste-based materials is simply that they don't have that environmental toxicity, and they do utilize waste streams, which doesn't reduce the environmental impact of producing those products and directing them into the appropriate waste stream. So just to wrap up, and please feel free to drop some questions if you have any more questions about plant waste materials or compostable products as well. But I just thought I'd share a little bit more about what the Waste Labs does. So our key services are really environmental performance, technical consulting, and R&D. We do whole systems consultation and also waste regeneration consultations as well to try to connect the waste creators with the waste users. We have developed a research space in the Falls Creek Flats, as I've mentioned, and we conduct standardized or custom research projects to incorporate best practices for product design. So we have these compost tumblers, which allow us to do disintegration trials. We use these innovative technologies that break down, use heat and agitation to facilitate accelerated degradation of organic materials. And we also have our growth chambers to do plant toxicity too. We work in partnership with urban farms to do larger scale compost studies, which are really fun. I get out there and actually get my hands dirty. It's one of my favorite things to do, is to dig through composting piles. And we also really love to translate our research into different types of public education resources to really start to facilitate conversations and engage stakeholders about these important issues. And so for us, we're really all about supporting the broader ecosystem to understand where circular bioeconomies can fit in and to start to bring these different stakeholders together to really start to drive more action and how we can incorporate these materials into our economy more effectively. And so please feel free to reach out to me and my team if you do have any questions about the waste labs and some of the work that we do. Thank you so much. I'll end it there.
Thank you so much for that wonderful presentation, Dr. Louise. It is indeed quite an area of research, how to integrate circular bioeconomy into our operations. And I'm glad that our participants, our attendees have someone to connect to in that regard. So thank you so much for that. Now we will move on to our next speaker, Dr. Amanda Joseph, who is a nature-loving material scientist working to create a plastic alternative from agricultural waste. She calls the new product that she has developed Grastic, a biomaterial made from the residual stalks of grass crops like corn or wheat. Dr. Johnson spent many hours in the field as a soybean breeder before coming to the UBC Faculty of Forestry to do her PhD. She is a UBC Sustainability Scholar, a public scholar, and the winner of the UBC Bioproducts Institute's Rising Star Award. She hosted a show about food farming and sustainability on Vancouver Co-op Radio. When not in the lab, she enjoys adventuring with her partner and 2 young kids. Over to you, Dr. Johnson.
Thank you so much for the introduction. I'm going to share my screen here. Can everyone see that? Okay, I'm speaking to you from Saanich in Greater Victoria.
I think we are not seeing the presentation now.
Oh, okay. Let's try again. Does that work?
Yeah.
Okay, perfect. I'm speaking to you from Saanich in Greater Victoria, and this is the it actually gets its name from the Wasanich peoples who have cared for the rich resources of this land and since time immemorial. So I would like to thank them and the Songhees First Nations for allowing me to work, live, and play on their lands. Okay, life is short, and I'm not going to be around forever. I'm going to give away my age and say that in about 50 years, I'll be gone. And that'll be it. My plastic water bottle, on the other hand, is going to be around for a lot longer than I will. 500 years, 1,000 years, 2,000 years, this is going to be in the environment somewhere because nature can't break it down. So of course, if I put it in my recycle bin, what's going to happen? Well, the lid is actually made of multiple types of plastic, and so it's considered a contaminant in the plastics waste stream. Recycling is not possible in this case. I think you may have heard the statistic, over 95% of what we put in our recycle bin isn't recycled. So it's probably going to end up in a landfill, an incinerator, or worst case scenario, contaminating our environment. Oops, I'm going to try and advance the screen. There. Yes, we have a very big plastics problem, and a lot of it is caused by single-use packaging. 40% of the plastics that were made last year went towards packaging materials that were meant to be used once and then discarded. So I'm talking about plastic takeout containers, plastic bags, and a plastic water bottle. I'm a material scientist, so I think about plastics on the nanometer scale. Plastics are made of polymers, and a polymer is a long, flexible, chain-like molecule that's made of the same unit repeated over and over. So this plastic water bottle is made of the polymer polyethylene. Now, you may say it works very well, and it does. We've done a wonderful job designing a material that maintains its structural integrity during transport, storage, and consumption, and protects the contents of it from the environment. We know it's harmful for our environment, though. And so it's time for us to start thinking about designing alternatives. This is Stephen Guilbeault. Anybody know him or have heard of him? He is the Minister of Environment and Climate Change. Last summer, he's in Quebec City making an announcement that the government of Canada is going to ban the import and production of single-use plastics. It's a great time to be a PhD student working on biomaterials, because here on his sign here, he's showing us what's going to be banned. Checkout bags, plastic stir sticks, 6-pack rings, cutlery, styrofoam takeout containers, plastic straws. And if you look at the bottom of his poster, he's proposing bio-based alternatives. So here we have a pressed fiber 6-pack ring, which you may be seeing in your stores, clamshells that are made from pressed fiber, and paper straws. Plastic bans like this could kickstart the circular bioeconomy that Lavesi was talking about, recovering value from biomass that would otherwise go to waste. And this is in contrast to what we're doing right now, which is the take, make, dispose economy. The circular economy is looking to decouple economic growth from our fossil fuel dependence and use biomass to make our materials. So to the core of my talk, biomaterials. Essie already talked about some types of biomaterials, and here they are. So we have I can't see the top here. The natural fibers, natural polymers. This is cellophane, so it's regenerated cellulose. Biodegradable, eventually. It takes a few years, but it is biodegradable. This is our PLA, so all the compostable bags you see in store are made from polylactic acid, which is cornstarch that's been fermented to glucose and then polymerized to polylactic acid. And finally, the last category of biomaterials is composite materials. So my PhD has been to develop a composite material made of natural fiber, cellulose, and another biopolymer. So I'd like to spend the rest of my talk telling you the story of how this came to be. But first, a definition. I already mentioned that a polymer is a long, flexible, chain-like molecule made of the same unit repeating over and over. A natural polymer or a biopolymer is simply a biopolymer made by living things. So cellulose is an example. Rubber is a biopolymer. Collagen is a biopolymer. Everything's, things owe their structural integrity to the biopolymers that make them up. So that's the definition of biopolymer. Now, speaking of biomass, this is a corn plant. Did you know corn was a grass? So all of our cereal crops are grasses. And grasses, in their stems, they contain up to 50% of a biopolymer that's called xylan. And of course, we're not talking about the food part. We don't have to worry about food versus packaging. It's purely the agricultural waste. 50% of the stalk of a grass plant is made of a biopolymer called xylan. And this is the biopolymer I chose to focus on for my PhD. And Anubhav mentioned that I came from the farm before I came to UBC. And so I saw a lot of this, harvesting the grain and leaving the straw or the agricultural waste tilled into the soil or baled off. Canada produces about 65 million tons of agricultural waste every year. And that's a lot of material that we could be using and upcycling into packaging material. I mean, if you want to talk about circularity in your food systems, let's harvest the grain and then harvest the straw and use it to make packaging for our food. So I went to the lab. I'd done a master's already on plants and biomass. So I had a kind of an inkling on how to separate the different polymers in biomass. So my PhD was really optimizing formulation of this bioplastic and testing its properties. So I found out a good way to get the biopolymer out of the plant. I tried different formulations, different processing conditions, different additives to come up with a bioplastic. After many failures, I came to the lab one time before Christmas break. I was going on a ski trip and I came to the lab to check how my films had turned out. And I was really stunned actually, because they had worked so well. I took the sheet of plastic and I held it up to the light in the lab, and it felt like a plastic sheet. So I was so excited. I called my brother in Ottawa and I said, I made a plastic. What am I going to call it? Because he's really good at language and puns and things. And he said, well, why don't you call it Grastic? Because it's made from grass. And I said, okay. So I called it Grastic, bioplastics from grass. And since the discovery of this material, COVID hit. Okay, so now I'm stuck at home self-isolating. I was stuck at home self-isolating, wondering what to do. And I thought the next logical thing would be to test how this material biodegrades. So I really needed someone who was exceptionally talented. And that's when I picked up the phone and I called Essie, who gave the talk before me. And I said, you've got to help me out. Can you test the biodegradation of Grastic? So Essie and her team at Regenerative Waste Labs developed they used a standardized testing method for measuring how Grastic biodegrades in composting material. So in the top of this slide are samples of compost taken every week. This is a piece of Grastic, and you can see that after 1 week, it's already completely colonized by a fungus. So this is a biomaterial that's very prone to breakdown. It has nature's recycling stamp on it. So by the end of 2 weeks, it's pretty much invisible. And all of this has been converted to carbon dioxide by 6 weeks into the test. And this is mimicking your home compost conditions. So at 23 degrees, it's as if you put a sheet of Grastic into your home compost. It would be gone by about 6 weeks. Since then, I've also tested the biodegradation of Grastic in the ocean. So putting it in seawater, whatever microbes are present, they biodegrade the Grastic. This takes a lot longer because seawater is at a lower temperature than soil, and there's a lower concentration of microbes in seawater. But Grastic biodegraded better than the positive control within 160 days in seawater. And just to give you an example, if you were to put a polylactic acid, PLA, bioplastic in the ocean, it would never biodegrade. And so it's really promising and exciting news that Grastic is biodegradable in the ocean. And again, in terms of the purely science perspective, it's very cool to measure how fast something biodegrades. And as bioproducts are gaining popularity, it's important that we have a way of measuring how they break down in the environment. So what is next? I will be testing the the coating properties of Grastic. So if you look at a typical beverage carton, it's made of several layers. Paper is for strength, polyethylene is often for water barrier properties, aluminum might be a light odor and oxygen barrier, and I suspect that Grastic could replace polyethylene in one or more of the layers of a multi-layer Tetra Pak. So the next step, I'm gonna test Grastic as a coating material. I've also applied for and been accepted into the Bioproduct Institute's Accelerating Technology Readiness Program. So this is basically a way to talk to seasoned entrepreneurs and have an advisory board, give you advice on de-risking the technology, because it's one thing to make Grastic in the lab, but if I'm talking about scaling it up to any pilot scale, there's a huge gap in knowledge or technology that's required. So I'm working on de-risking the technology. In conclusion, it took me 4 years to develop this biomaterial from agricultural waste, and I think it's a really it's a really good story. It tells us that we don't have to accept the status quo of, fossil fuel supremacy in our society. If we put our minds to it, we really can come up with alternatives to single-use plastic. So to wrap up again, in 50 years, I might be gone, but I hope the research that I do has an impact so that one day we'll all be able to go to the store and buy our food packaged in Grastic rather than in plastic. Thank you.
Thank you so much, Amanda. What an inspiring presentation. It was really wonderful to hear about your invention and how you are trying to take it forward. We hope that currently the industry is suffering with this ban coming in for the supply of a valid material that can really replace plastics. And I think your research is a step in the positive direction. So best of luck for your future. With this, now is the time for the Q&A portion of the webinar. We will be asking our panelists some questions as well as any live audience questions that we might receive. So if you have not already posted your questions, you can go to the Q&A panel at the bottom of your screen and post your questions. So with this, maybe we can start off with the first curated question, which was how we can make sure that the biomaterials that are coming in are not harmful throughout their life cycle stages from production, use, disposal, degradation. So maybe that is a question for both of you, maybe Dr. Louise and Dr. Amanda.
Yeah, thank you. Sorry, could you just repeat it again? I just missed the first part.
How can we make sure that these biomaterials are not harmful throughout their life cycle stages, from production to use to disposal to degradation?
Yeah, that's a fantastic question. And I think it comes down to testing and standardization. Yeah, so I mean, many companies, especially those who are making plant and waste-based materials, are doing things like life cycle analyses to understand the actual production side and the environmental impacts of the energy and water, especially, and the GHG emissions. I think one of the benefits of using locally produced waste streams as feedstocks for these types of materials is that you're now able to localize both your consumption and your production, and that will then minimize the amount of transportation and GHGs related to that. And so that is an additional benefit and an opportunity. I think on the end of life side, there are standardized test methods to understand how these products do break down in composting conditions. I think there is definitely opportunities or space for more work to be done for in things like the soil and plant toxicity of the compost that's applied into the environment, as well as if products do end up being littered in the environment, which is obviously not the disposal mechanism that we need, but it is a problem of our society and our throwaway society that things do end up in the environment. So I think more testing and more validation of products is really important. But I think the caveat there is that all of that testing takes time and money. And so what's really quite a challenge in the landscape is that you see people like Amanda making plant and waste-based materials, but then having to spend or invest so much more to make sure that they are truly sustainable. Whereas on the other side, any company can make a polyethylene and just put it out there without having to do the same type of validation. And so that means that these products are much more expensive than the incumbents, which makes it very challenging, both for businesses who are starting up like Amanda's, but also for the procurers and the people who want to purchase those alternatives. They now have to spend more money to have a sustainable alternative, and that's really one of the biggest challenges for switching over to sustainable, which I think is a really big challenge.
Yeah. Would you like to add anything, Amanda?
I have nothing to add. That was well said.
Maybe the second question, maybe you may be in a better, and obviously Dr. Louise is also in a better position to answer. So this is around how can the use of biomaterials in food packaging be incentivized and promoted through government policies and initiatives? Do you have any suggestions around it?
Ooh, how can it be done? I think it's important that the government is on board. It's absolutely critical. I went to a takeout restaurant, or I went to a restaurant one time, and the owner of the restaurant told me that the paper fiber clamshells cost something like at least twice as much, if not more, compared to the plastic. So yes, it absolutely has to be incentivized, because no business owner wants to spend more money.
Well, 5 times it costs.
Is it 5 times? Okay, so yeah, so it absolutely requires government incentives. But I think, yeah, I think across the board, leaders and politicians are making commitments to be greener with their packaging. So I think once we ban certain items, early adoption will occur, and this will fuel the economies of scale that we need to make our bioproducts viable.
Thank you. Would you like to add anything, Dr.?
Yeah, I think Amanda's exactly correct. We need to somehow flip the incentives around, because I think for pretty much all business owners, if you're a for-profit company, the challenge really is it comes down to dollars and cents. And if there's no viable alternative, or if the sustainable alternative is going to cost you 5 times more than the unsustainable incumbent, what is the motivation for businesses to invest in that? And then you have this trickle-on effect that cost gets passed on to the consumer. And then once again, we also see these challenges already with inflation from post-COVID kind of recovery. But now that if we're wanting to then step into a green recovery, and that's going to cost consumers even more, it's just going to end up being completely unrealistic. And so we need to find a way to flip that switch, find incentives for businesses to adopt sustainable alternatives compared to the conventional. But that really does mean bringing the stakeholders together to have conversations about how to really facilitate that action.
Thank you so much. Maybe we will come on to the certification side of things, because consumers are quite worried about the applicability and safety of these materials. So do you know about, is there anything that Canada is working on their own certification stamps regarding recyclable biodegradability, or we are just using the US certification agencies to keep it congruent?
Yeah, that's a great question. And so the Canada does have a standardized test method scheme, which is I guess facilitated through BNQ, which is the Canadian standardization organization, which is a weird thing. But it is in alignment with both the US and international standards for compostability. So there's a need for that harmonization across jurisdictions, because businesses aren't just selling to Canada, they're often selling into the US and selling to global marketplaces as well. And we also want to make sure that businesses which are selling into Canada also are aligned with the same standard. There are challenges with the certification standards. If anyone's been on any type of committee, the standards are made through committee action. And so it can be slow to update and change standards. And that may be what is needed to continue to raise the bar on certain compostable products. But that harmonization is definitely needed to ensure that all of the products coming with that stamp of approval have the same performance, so that you do have an even playing field.
Okay, maybe we will move on to the next question, and maybe this is more to Dr. Amanda. Are there any health risks associated with the use of your material in bulk, for example, that comes from the grass? And maybe a more general question to Dr. Shiel around the use of other biomaterials. Are there any health risks that are associated with using them in bulk?
Using them in bulk, like the scale up of Grastic production?
Yep.
I can't. It's completely safe. I told the Vancouver Sun reporter that I've eaten it, and it tastes like nori that you wrap sushi in. It's very safe. It's made from biopolymers, and mainly I use water to extract it. So I'm quite sure it's safe. SE verified that it is biodegradable, and so I haven't tested, for example, the grasses for heavy metals or anything like that, which probably is a good next step. Although I have done elemental analysis. Essie, that would have shown up in the elemental analysis, right? If there was cadmium in the Grastic.
It depends on what the analysis is, but we could talk more offline for sure.
So yeah, so I mean, yeah, I guess further testing could be done, but as far as I know, it's I don't see any health risks associated with large scale production of Grastic. It's all water-based extraction.
Yeah, and do you have any comments on other biomaterials which are being currently brought into the production cycles? Maybe Dr. Levy's.
Yeah, that's a fantastic point. And honestly, there are so many plant and waste-based materials entering the landscape today, all the way from products extracted from grasses like amandas to things which are made from like chitosan, made from shellfish waste. Yeah, there's like the world is your oyster when it comes to bio-based and plant-based materials. What I will say about the toxicity and the potential long-term impact is that if you have a certified compostable product, they have to have done the heavy metals and fluorinated tests to ensure that there are no heavy metals or fluorinated compounds in those products. And so even though the end of life for compostable products is challenging, that landscape is quite complex, and there are a lot of stakeholders with varying things to say about compostables for when they go into the composting pile. There is something to say that conventional plastics and conventional products do not get that type of toxicity testing. And so by being able to choose certified compostable materials, you are sure that that product is going to be benign for the environment with regards to the compounds that are inside of it. So even if it does end up in a landfill or end up in the environment, we know that at least it won't be leaching out toxic compounds into those ecosystems. So obviously, the end of life is a substantial part of the life cycle analysis, and ensuring those products actually go into the compost pile is imperative to closing the loop on compostable products. But and one of the great things about Amanda's process is that it's utilizing green and sustainable chemistry. So no toxic compounds to do that extraction. And the only real challenge I think that Amanda will have as she moves forward is to figure out how to scale up the extraction. But as long as people are incorporating those principles during that design and development phase, and we know that they're going to end up with the right result because they're just making sure that is a key performance indicator for the project or the program as it keeps going.
Yeah, okay. Maybe some like people are really getting excited about Grastic around the esteem. So here's a question from Dr. Coleman around is Grastic patent protected? And also a follow-up from another anonymous attendee around would Grastic be suitable for replacing single-use items in a medical institution setting, such as gloves, syringes, etc.?
Okay, is it patent protected? Yes, we're in the process. We don't have a patent yet, but we have an invention disclosure, soon to be a provisional patent. Would it be suitable for gloves in the medical industry? It would not be suitable for gloves because it is not waterproof. So being a biodegradable material, it is water resistant, and I have been able to increase its water resistance to the point where it does very well with water. But again, if you leave that water on for several hours, it will soak through. So it's not suitable for yet, I mean, as it is for a medical glove application. But I also see in the chat, someone had asked whether Grastic wrap would degrade in the fridge. So again, biodegradation will happen if the right microbes are present and if a lot of water is present. So in the fridge, yes, it would take longer, as someone else said on the chat, but it would probably biodegrade in your fridge, or if the microbes were there and if a lot of water was there. Yes.
We have more questions coming in. So this is from Oliver Nerger. Do you think at one point society might be asking as well for organic plant-based packaging? I mean, is there a concern for using agricultural waste from an unhealthy farm to create a product that will be composted and eventually be be used in our gardens that grow our food. I think Love is touched on the testing already, but Oliver was actually looking for your thoughts on this. Dr. Amandas, this was a question for you. Do you think that at some point in the society might be asking for organic plant-based packaging as well?
Yeah. Wow, this is cool. I mean, I feel like I'm preaching to the choir a little bit, because everyone that's at this webinar is probably very interested in sustainable packaging. I think it's a wonderful idea. But I mean, yes, let's do this. Let's develop this technology to the point where yeah, it's viable on a large scale. And then yes, I'm excited when people start asking for organic based. The grass that I use to develop Grastic, I've tried many different grasses, by the way. I've tried flax, rice, wheat, and another one called esparto grass from Spain. The esparto grass I used was organic, and I don't know about the other 4. So, I mean, right now on the lab scale, I can do organic, but yeah, we'll see when we reach the pilot scale what I'll be using.
Another question which is coming in is, do you think that Grastic will be used within the industry? How close is it? How many years away, for example?
And that's why I'm in the Accelerating Technology Readiness Program. So I have an advisory board that's helping me figure out how to get it going. When you start a product, you're usually going for like a niche market, something that's higher value that will give you enough capital to get going and scale it up. So I'm looking towards, you know, niche applications or small projects. But we've been approached by you know, I don't think I'm allowed to disclose their name, but major food manufacturers who are interested in using Grastic, because everybody wants to show that they're green. You know, 86% of people between the age of 18 and 44 say they're willing to choose the product that's in sustainable packaging. So these companies want to respond to the consumer pressure to be green. And so I have been approached by large food manufacturers that want Grastic to be used as films in their maybe bakery products or pasta boxes or ice cream, like the film over an ice cream carton. And at this point, I have to say, I can't do that yet, but I really want to do that soon. And so again, it is the perfect time to be developing a bioplastic, because this is it's a hot topic right now. Plastic is a very hot topic. So yeah, I don't know. I hope to scale it up very soon.
Thank you so much. Maybe we have time for one last question, and it is an open question for both the panelists. What role can consumers play in promoting the use of biomaterials in food packaging? And how can we educate them better about the benefits of these materials over conventional ones? Maybe Dr. Louise first.
Yeah, that's a fantastic question. I think one of the biggest challenges is that consumers are at the end of the supply chain. So their main responsibility is directing packages to the appropriate end of life waste stream. So you can decide whether your product goes into the recycling bin, the garbage bin, or your green bin. But that's a limited space. And I think one of the biggest challenges really is we need more eyes on waste. And so you often don't see politicians or policymakers really standing on a platform of waste. It's not really, one of the bigger talking points. But I feel like if we're really wanting to implement a circular economy, we have to bring the challenges and limitations of our waste systems to the forefront. Even just kind of trying to track down where Metro Vancouver is sending their organic waste is a challenging thing to do. And so I feel like as consumers, as individuals, as community members, it's very challenging to access that information. And so some of the best things to do is to go to your local representatives and just say, hey, this is an important issue to me. We need to talk about it more. We need to come up with solutions to actually facilitate the use of bio-based materials and the recovery of those materials in the appropriate waste stream as well. So I definitely recommend that as a good avenue to kind of continue to build out this industry.
It is very hard to track down where our waste and recycling goes. I have tried, and contacting my local landfill, they're suspicious of me. Like, what are you doing? Are you going to like stand outside with a sign making us look bad? It's a lot of suspicion, and I agree. Let's bring this to the forefront, and I would love more transparency. The problem with plastic recyclings is often it's based on, is there a market for this recycled plastic? So it might change from day to day. Maybe today, if I put a bottle in my recycling bin, it'll be, you know, recycled, and maybe in 2 months from now it won't be. And so it's hard for them to be transparent with consumers when it's just so confusing, even to them.
Yeah, thank you so much. With this, we would like to wrap up. We thank you all for sharing your time with us and helping to move our food system forward. We will send up a follow-up email where you can send us any further questions, or you can reach out to the panelists directly at the emails provided within the chat. Thank you to both our presenters, Dr. Laviz and Dr. Amanda, for sharing your insights and your time with us. Behind the scenes, we would like to thank Melanie, Akila, and Juliana for their very hard work and for putting up this webinar series together. Join us virtually in 2 weeks for our 4th episode entitled Finding Unity, Integrating Environmental Health with Food Production on March 9th from 11 a.m. to 12:30 p.m. PST. Let us know about your thoughts about the webinar. You will be directed to a short survey about this session after the webinar, and we will really appreciate your feedback. Also, feel free to visit us at ubcfarm.ubc.ca. Thank you for joining in, and we look forward to continuing our discussion together. Thank you so much.
Thank you.